Hi, thanks for clicking on the video. In this one we will cover how you can fix an integration that looks like this here, where we have a step in the input, we expect an outcome that looks like the one shown on screen, but our integrator returns this absolute rubbish here. If you have this problem and you are just looking for a quick and dirty way to fix it, feel free to skip to the timestamp shown on screen. To give you an overview what you see here, we will first cover the model of the simulation and look at the system equations. Then analyze where the problem originates from here. Afterwards I show you two ways with which you can fix the issue. A quick and dirty one, where you pay the fix with calculation time, and afterwards a better version where we still take a bit longer to calculate, but not as much as with the quick and dirty version. And finally, an outlook what comes next on the channel. We have this vehicle affected by air resistance and pushed by its engine. This is the same model that was used in the second video of this channel. I've linked it in the description if you need more details. In the simulation shown here, we have an input signal that can jump. So at first our engine is at full power and it is used to propel the vehicle forwards. Then we brake, then propel again and then brake again. If we just implement our equations of motions like this here, without any extra steps, our simulation will be absolute rubbish as you have seen before. I showed it at the start, but let's look at it again quickly. Running the simulation, we expect something like this here. Every time we have positive power we accelerate, and since we switch abruptly from positive power to negative power, we also expect a sharp edge before decelerating again. But if we just run the simulation without any additions, we will see that the result looks more like this here. You can actually try it, the code is in the video description. Up to a certain point, the simulation is the same and looks quite good. But near the first power change, something odd happens, leading to quite a big error from this point onwards. Let's analyze this closer. We zoom into our first acceleration change up here to analyze what is happening. First, we slowly shift our time point when the acceleration is switched from being positive to negative and look at the result. As you can see, our simulation does not exactly do what we want. For quite some times there are no changes, even though the input signal changes. Then our simulation result abruptly changes and this repeats over and over. This behavior comes from the inner workings of the Ode45 integrator. If you remember from the last video, the integrator figures out the time step between integration steps on its own. Then evaluates the ODE function at the intermediary points and interpolates the state to give us our final result. If we now visualize the intermediary points with solid dots and the nodes between two time steps with those crosses here, we can see something interesting. We now change the point when we decelerate backwards and forwards again, and see that as long as the switch happens between two intermediary points, the outcome does not change. From the perspective of numerical mathematics that is performed here, the Ode45 does exactly what it should. It evaluates the ODE function at the nodes, calculates what the change should be, and then interpolates the result. Our problem here is that it does not consider the switches correctly. For an interval like this here, the switching is exactly between two nodes. The first ODE steps here use the positive input, then the points back here the negative input, and for the interpolation performed to reconstruct the state, all of the points are used. And the outcome you see on screen is the numerical result to this. Now, the closer an actual integration node is to the switching point, the smaller our error is as well, as you can see with this result here. This further means that we only have to find a way to get our integration nodes to line up with the switches in power, and our simulation result should be correct again. There are multiple ways to do this. The first one is the quick and dirty one, where we forcibly limit the maximum step size of the integrator to get the nodes to be closer. And the second, where we use event handling to find the exact points and then adjust the simulation to start and stop at those exact points. But more to that one later. For the quick and dirty fix first. Just add an ODE option structure like this here, with the maximum integration step size to be rather small, and you cannot tell the difference, except if you zoom in a lot or if details actually matter. But that is the quick and dirty version. If you skipped ahead and this fixes your issue, make sure to tell me in the comments and give the video a like. Remember, you must add this option structure here like this, because just adding this here only affects the interpolation of the results and has zero influence on the actual ODE step size. If this is too inaccurate, or if the simulation time is too long for you now, because forcing a very small step size comes at considerable computational cost, you might need to take the slightly longer way following next. But you can copy the code for it from GitHub, so it should be rather quick to implement as well. As we have discovered previously, we only have to detect when our acceleration switches from positive to negative, and then we run the simulation on the exact intervals in between. To avoid reducing the ODE step size to be too small, we can do the following. First, we use event handling like this here to detect when our switches occur. Here, it only depends on time, so we do not have to stop the simulation. Afterwards, we read out when our event got triggered and prepare the new simulation start and end times like this here. Then we prepare a vector for our simulation time and state. Afterwards, we run the simulation stepwise, always on the intervals discovered with our event handling. We loop over all of our intervals with the same steps each time. Get the start and end time. Here we reduce the endpoint slightly because it leads to cleaner results. We know that the switch of acceleration occurs directly at the endpoint, and doing it like this avoids using the incorrect acceleration at the last ODE step. We then define our time vector that should be used for the interpolation. Be careful here, for each step this one has to start at 0, which is why we subtract our interval start point back here. Then we run our integrator, being careful that, as far as the simulation time is concerned, we start at 0 and we actually compensate for the actual start time up here. In the last step, we concatenate our results to have a single vector containing the simulation. If we now look at the simulation result, we see that we managed to fix our simulation errors. Since the result calculated with this method was the correct simulation from before, you have already seen the results. This simulation now behaves exactly as it should. As long as our power is positive, we actually accelerate. If it is negative, we decelerate, and most importantly, our changes are actually correct. Bit of a quicker one this time. The code is linked in the video description if you want to play around with it by yourself. The next video will most likely be on Lagrange's principle and how to formulate system equations with it. Other than that, thank you very much for watching. Like, comment and subscribe. Bye for now. See you next time.